Okay guys, I'm going to share some solutions with you. So let's take a look. This is for your student notes, pages 21 to 22. Yeah, so we'll try to keep this short and sweet, see how it goes. Okay, first one. First thing we need to recognize here is that when we look at this 9 volts here from our power supply, that is all voltage that is going to be consumed by the rest of the circuit. So it's a conservation law. So the energy provided here is going to be used. And it's described as one of Kirchhoff's law, where the sum of voltage is equal to 0 in a circuit. Particularly this kind of circuit. So we've got here a 9-volt power supply. 5 of those 9 volts are consumed by our first component, leaving 4. Okay, so that's going to eat up 5 of those volts, leaving 4 volts left. The second component, we're given 2 volts, so that is going to eat up another 2 volts, and that's going to leave a total of 2 volts remaining for our last component. Okay. So here's a mathematical representation of that. Okay, if we know the voltage to a circuit, then, and particularly the voltage of a given component, as well as the current going through that component, then it's really easy to calculate the resistance. So our first component, we measure the voltage across it, we get 5 volts, and we divide that 5 volts by 7 amps, and that will give us 0.7 ohms. Okay, we then repeat that process for our second and third components, and it's really easy because they have the same current and voltage, and we get 0.3 ohms. So there they are. Okay, the brightest bulb is the one with the largest voltage in this series circuit, because power is equal to voltage times current, and current is constant. So our 5-volt bulb there is going to be using up the most power and releasing it as radiation and energy. So bulb 1 is brightest. Okay, next you are asked to use your understandings of the nature of series and parallel circuits to determine the values of the missing readings. Okay, so let's have a look here. First, in order to find the current here, we need to look at this current and this current, okay? Because, and this is another of Kirchhoff's laws, the sum of current into a junction, and that's just anywhere where wires meet, this guy, is going to be equal to 0. So what that means effectively is that the amount of current going into the junction, I sub 1, is equal to the current coming out of the junction. Okay, so what that means is I sub 1 will be equal to I sub 2 plus I sub 3. And we know those values are 1 amp and 3 amps, so that gives us 4 amps. Okay, that's going to be true on the other side as well. Okay, so I sub 1 on the other side of the circuit is also going to be equal to 4 amps. And that's going to be important a little bit later. All right, the next thing we need to recognize here is we have a parallel circuit, but this guy is going to be using up a lot of the voltage available to our other 2 components. Okay, so much like our series circuit, we can consider the first loop to be, at least in some ways, similar to our previous example. Okay, so we've got 9 volts leaving our power supply. Oops. And that 9 volts in this loop has to be consumed by all the components. So we know that 3 volts is already being used up. So that leaves 6 volts for this guy. Okay, and it's the same situation for our second loop. Remember that normally the second loop would have basically direct access to the battery. However, we treat the second loop and this component as if they're in the same loop. And as you can see, they actually kind of are. Okay, so if you imagine this as now one loop, then there you go. It all makes sense, doesn't it? Okay, so what that means then is that the voltage across both bulbs is going to be 9 volts minus 3 volts, as I have written here. And that will be equal to 6 volts. Okay, once we have that information, we now know all of our currents. So calculating resistance using Ohm's law is very straightforward, as you can see here. And I probably don't need to go through it. Okay, explain which bulb is the brightest. Here I've actually calculated the power for each one. So using our formula for power, where power is equal to current times a potential difference, we have 12 watts for our first bulb, 9 watts for our second bulb, and 18 watts for our third bulb. So that is going to be by far the brightest bulb. All right, quick mistake, quick update. This should be 6 volts. My bad. Okay, so that's going to give 6 watts. There we go. Sorry. Okay, moving on. Bulb 3 is the brightest, consumes the most power. There you go. Hopefully you're watching this on double time and that did not take very long. Okay, I actually copied this guy over to here because I just wanted to do a little bit of math and kind of spread things out and make it more clear. So, yeah. First up, we know that A sub 3 for circuit B is equal to 6A. And remember, we were told that we should generally assume that the bulbs are identical. So here they've actually stated it. I'm not quite sure why, because we've already been told to assume it. All right, so for A sub 3, we have 6 amps because it's in the identical position on the other side of the circuit. So easy. Second one, A sub 1 is going to be equal to A sub 2 if we assume that our bulbs are identical. So I have then decided to call them both equal to A sub 1, 2. And if we then take a look at A sub 3, we will find that A sub 3 is going to be equal to the current of A sub 1 and A sub 2 for reasons that I've already explained. What that then means is that A sub 3 is going to be equal to 2 times A sub 1, 2. And we know the value for A sub 3. So we will find that the current through each of our unknown bulbs is equal to 3 amps. Okay, what can we say about the bulbs? Well, we can say they have different resistances. What we can also say is that A sub 1 is going to be equal to A sub 2, and both of those will be the sum of these two currents. So 9 amps is our missing values for both. Okay, next up, here we have a parallel circuit. I've stated that V sub 3 is approximately equal to 0. And that's because if we wanted to get really picky about this, this little section of wire here is actually going to have a very small amount of resistance. And if I wanted to be really, really, really picky, you could say that it's not exactly 0. It's going to have a slight voltage. But anyway, so V sub 1 is equal to V sub 2, and I have called that V sub 1, 2. I then add my voltages together, and I get 9 volts per bulb. So this is a series circuit, which means that the components are going to split the voltage up between them, and that's what we see here. Okay, next one, just an extension of the previous idea. Here we have 3 components evenly dividing the voltage, so divide by 3, and we get 6 volts for each component. Okay, for V sub F, as I stated before, each of these components basically has direct access to the power supply, or the battery in this case. So each of those voltages will be equal to 6 volts. Okay, getting a little bit more complicated now. We have series and parallel components in our circuit. So first thing we recognize is that our parallel components are both going to have full access to the battery effectively, and that means that the voltage across V sub 1 and V sub 4 is equal to 8 volts. Okay, from there, if I know the voltage for V sub 4, I then just treat this little part of the circuit as I would treat any series circuit. And my light bulbs of equal resistance are each going to consume half of the available voltage. Okay, so we take that 8 volts and we divide it by 2 and get 4 volts for each of those components. So V sub 2 and V sub 3 are equal to V sub 4. Okay, next up we have H. We have another parallel series circuit, and this one actually looks a bit like one we already looked at earlier. So we have this parallel component of our circuit, and then we have the series part of the circuit as well. So basically what's going to happen here is V sub 3, which I've drawn here, V sub 3 is going to be the voltage across V sub 1 and V sub 2. And both of those will actually be equal to V sub 3. So V sub 3, however, is in series with our light bulb. And our light bulb is consuming 18 of our 24 volts, which means that there's only 6 volts left for V sub 3. And because V sub 1 and V sub 2 are in parallel, they will be equal to 6 volts as well. Okay, next. Last one. So here we have to add up our series and parallel voltages, much like we did in our last circuit. So our parallel voltage in this case will be given by V sub 3, okay? And we are given 1 volt for this component, and we are given 1 volt for this component. We also know that all of our components have equal resistance, okay? So what that means is that all the bulbs in the parallel part of our circuit are going to have a voltage of 1 volt. Okay, so for V sub 3, if I measure the voltage across those two, I'll find that it is equal to 2 volts. So just 1 volt plus 1 volt is equal to 2 volts. Okay, so that will give me then the voltage across the parallel part of our circuit, which would be from these 2 dots that I've now drawn on here. So if I put a voltmeter across these 2 dots, what I will find is that that voltmeter has a reading of 2 volts. Okay. All right, so we then look at the other components here, and if the voltage across this bulb is 2 volts, and we know that our bulbs are equivalent, then the voltage across the next series bulb must also be 2 volts. Okay, so then I add up all of those voltages, the series voltages and the parallel voltage, and I will find that I have a total for V sub 4 of 6 volts. Okay, that's it, guys. This does take a little bit of practice. Hopefully you found it reasonably straightforward, but let me know if you did not. Let me know if you have any questions, and I will talk to you soon. Have a good day.